The single most undervalued fact of linear algebra: matrices are graphs, and graphs are matrices. Encoding matrices as graphs is a cheat code, making complex behavior simple to study. Let me show you how. We can figure out the rule by looking at this example. The elements in the first row correspond to edges outgoing from the first node v1. First, a loop edge to itself with weight 0.5, then an edge to v2 with weight 1, and no edge to v3. Edges of zero weights are omitted. Similarly, the first column corresponds to the edges incoming to the first node v1. Again, a loop edge to itself with weight 0.5, an edge from v2 with weight 0.2, and an edge from v3 with weight 1.8. In general, each row of the matrix represents a node, and each element represents a directed and weighted outgoing edge. Because of the construction, each column represents the incoming edges. This is called the directed graph representation of a matrix. Why is this beneficial for us? Let me show you. This is the story of matrices and graphs. To see what graphs show about matrices, let's talk about the connectivity of directed graphs. This is a strongly connected graph. In general, a directed graph is strongly connected if every node can be reached from every other node, like in this example. The word strongly refers to the fact that we are dealing with directed graphs here. On the other hand, if not every node can be reached from every other node, the graph is not strongly connected. For instance, our example graph right here is not strongly connected because there is no path from node B to node A. Even though this example graph is not strongly connected, we can still partition the nodes into strongly connected components, meaning that we can group the vertices into disjoint subsets such that every subset is strongly connected in itself. Here we have two components. The first one is colored yellow, while the second one is colored blue. We can do this for all directed graphs. I won't go into the details here, but this is because the B is reachable from A is an equivalence relation. Let's see how connectivity relates to the deep structural properties of matrices. First, the strongly connected case. After appropriately labeling the nodes, we can easily find the matrix representation of our directed graph. For simplicity, I have assumed that all weights are 1. Second, the not strongly connected case. This is the interesting one. Again, after appropriately labeling the nodes, we can find the matrix representation. So, why is this interesting to us? If you are well versed in linear algebra, you'll notice that 3x3 block of zeros in the lower left corner. This is our first hint at the deep underlying structure of matrices that are about to be unlocked by the connectivity of their directed graphs. Let's take a detailed look at this 6x6 matrix. It can be decomposed into 4 3x3 blocks, each one corresponding to a specific section of the graph. The one in the upper left corner corresponds to the edges within the first strongly connected component, and similarly, the lower right corner represents the second component. On the other hand, the non-diagonal blocks represent edges between components. The upper right block corresponds to edges from the first component to the second, while the lower left block corresponds to edges from the second component to the first. As there are no edges from the second to the first, this block is full of zeros. In other words, this matrix is upper block triangular with square blocks. Now we are ready to talk about the structure of matrices. Matrices that can be written in an upper block triangular form with square blocks along the diagonals are called reducible. Otherwise, they are called irreducible. We can push the idea of reducible matrices even further. This upper block diagonal matrix structure with irreducible square blocks along the diagonals and reducible matrices above the diagonal is called the Frobenius normal form. Let's reverse the question. Can we transform an arbitrary non-negative matrix into the Frobenius normal form? Yes. In general, if A is a non-negative square matrix, then there exists a special matrix P such that P transpose times A times P is in Frobenius normal form. With the help of directed graphs, this is much easier to prove than purely using algebra. For that purpose, let's look at the special class of permutation matrices. This seems like a random detour, but it will all come together in the end. Let's look at a special case. What happens if we multiply a 2 by 2 matrix with this P right here? A simple 0-1 matrix. With a quick calculation, you can verify that multiplication from the left switches the rows, and multiplication from the right switches the columns. Multiplying by P from both left and right compounds the effects. It switches rows and columns. By the way, this is a similarity transformation, as our special 0-1 matrix is its own inverse. This is not an accident, more about it later. Why are we looking at this? Because behind the scenes, this transformation doesn't change the underlying graph structure, just relabels the nodes. In our example, the two nodes v1 and v2 simply switched labels. A similar phenomenon is true in the general n times n case. Here, we define the so-called transposition matrices P, I, J by switching the ith and jth rows of the identity matrix. Transposition matrices have a number of pleasant properties. They are invariant to matrix transposition, their transpose is their inverse, and most importantly for us, multiplying with them from the left switches rows, multiplying with them from the right switches columns, and doing a similarity transform with them switches the labels of two nodes in the corresponding graph. Now it's finally time to talk about permutation matrices. A permutation matrix is simply a product of transposition matrices. What's most important for us, a similarity transformation with a permutation matrix is just a relabeling of nodes that leave the graph structure invariant. Conversely, every node relabeling is equivalent to a similarity transformation with a well-constructed permutation matrix. Why are we talking about this? Because the proper labeling of nodes is key to transforming a matrix to the Frobenius normal form. Now, let's talk about graphs. We'll see how every directed graph decomposes into strongly connected components. For that purpose, let's see a concrete example. How many nodes can be reached from a given node? Not necessarily all. Say, from the one at the bottom right, only a portion of the graph is accessible. However, the set of mutually reachable nodes is much smaller. Algebraically speaking, the relation the nodes A and B are mutually reachable from each other is an equivalence relation. In other words, it partitions the set of nodes into disjoint subsets such that two nodes from the same subset are mutually reachable from each other, and two nodes from different subsets are not mutually reachable. The subsets of this partition are called the strongly connected components, and we can always decompose a directed graph in this way. Every edge is either inside the component or between two components. Now let's connect everything together. We are two steps away from proving that every square matrix can be transformed into Frobenius normal form with a permutation matrix. So here's the plan. First, construct the graph for a non-negative matrix. Second, find the strongly connected components. Third, relabel the nodes in a clever way. And that's it. Why? Because as we have seen, relabeling is the same as a similarity transform with a permutation matrix. There's just one tiny snag. What is the clever way? I'll show you. First, we skeletonize the graph. Merge the components together, as well as any edges between them. Consider each component as a black box. We don't care what's inside, only about their external connections. As a result, we have a directed and a cyclic graph, thus we can order its nodes in a sense. The rule: if there is a path from node A to node B, A must rank lower than B. This is called a topological order, and it always exists on directed acyclic graphs. Now we can finally label the nodes of our original graph in a way that respects our topological order. If the graph itself is coming from an actual matrix, such relabeling gives the Frobenius normal form. Here is the matrix in this particular example with zeros and ones for simplicity. First, we have the edges of the first component, of the second component, from the first to the second, of the third component, and so on. With that, we have proven that every non-negative square matrix can be transformed into Frobenius normal form. P is simple to construct. It's just the permutation matrix corresponding to the relabeling of the underlying graph. This is quite a powerful theorem, with a visual and intuitive proof made possible by leveraging the connection between matrices and graphs. Such deep structural results, like the spectral decomposition theorem or the singular value decomposition, are the pinnacle of linear algebra. There's much more to this connection. With linear algebra, we can translate stochastic processes into matrix products, or even define eigenvalues for graphs, but that's a topic for another day. If you have enjoyed this video, like, subscribe, and consider supporting me via a channel membership. I'm an independent, audience-funded content creator, and your support makes videos such as this possible. Thanks for watching, and see you soon. Cheers, Tivadar.